So a brief look at multimedia data. This is an easy section and we will begin. Text and static data is the first multimedia kind, is the first media kind. This is an unformatted text, for example here. You can see all characters have the same style and font and their pitch is the same. The advantage is vertical alignment is easier. However, you cannot do a lot of things with this unformatted text. That's why you have something called rich text, which are which is text with characters that can have different styles and their pitches is variable, and they may also respect certain formatting rules. A second type of media is the graphic. You can represent an idea not only by writing a text. There is another media to represent your ideas, which is graphics. Graphics is different than images. Graphics that have their own format. It is a composition of primitive objects. A graphic is nothing else but a set of lines, polygons, circles, curves, arcs. They are drawn, either generated by a program or automatically generated using um, for example, an application. So either the user decides to do this graphic, or you have another document and you want to transform it into a graphic. The graphics are editable and revisable, unlike images, because this is a composition of lines and polygons and circles, etc. So you can change the composition easily. And input devices for this type are keyboards, text and cursor controls to write instruction like a C program, for example, or mouse, trackball, graphic tablet in which you draw your graphic and it will be digitized. There exists standard for graphics and the files store primitive assembly and the storage size is small. Images, this is an image, for example, a very small image, and we zoom it to see it. Images are still pictures, uncompressed, on the uncompressed form. They are bitmaps. What is a bitmap? It is a map of bits, so a grid of pixels, where you can see here each pixel either is white, blue, dark blue, or red. This is an image. So we can consider, or we do say that a pixel is a picture element. It means picture element. So the input of images, how do we get them? How do we enter them to the system? They are digitally scanned, either from a digital camera, either from a scanner, or generated by programs similar to graphics or animation programs. Those also are another images, other types of images and other example of images. We see here a black and white image. Look with me. Every pixel is either a black pixel or a white pixel. There is no other option. So to store this kind of bitmaps in the computer, we only need 1 bit per pixel. This bit will be 0 if the pixel is black and will be set to 1 if the pixel is white. And of course, it will take a small size in the memory because it needs only 1 bit per pixel. A grayscale or color map image is this mandrel image example. It is not only black or white, it is also grayscale image. You can see different level of grays. So in order to represent each one of the pixels, we need 8 bits per pixel. So every pixel is stored on 8 bits. So how many colors for each pixel we can have? 2 to the power 8, 256 possible colors for each pixel. Of course, all these colors are gray levels, so are gray colors, but they differ in levels. And we have other type of pixels, which are, for example, true color. Look with me, there is lots of color, lots of shades, lots of intensities. And for example, the pictures, the images we call true color, they are encoded using 24 bits for each one of the pixels inside them. Okay, 24 bits divided by 8, it means 3 bytes. Bits and bytes, let's remember that one capital B is 1 byte, is equal to 8 bits. And when we say 1 kilobyte, we mean 1000 bytes. And when we say 1 megabyte, it means 1000 kilobyte. It means 1 million bytes. And then we have 1 gigabyte, which is 1000 megabytes, 1 million kilobytes, or even 1, I don't know, billion bytes. Why do we remember those things? Because we want now to take a look about the sizes. Let's consider an image with 512 and 512 width and height, and which is a grayscale image. So we continue. This is an example we will be taking. We will consider, we want to calculate now the size of a grayscale image. As I already explained, this is a grayscale image, not this one, neither this one. This is a grayscale image. So every pixel in a grayscale image will occupy 8 bits. We have 8 bits per pixel. The width of the image is 512 pixels, and the height is 512 pixels. It means we are considering a square image, a grayscale square image. And now we want to calculate the size of this image. Before we calculate the size of this image, let me take you to see a grayscale square image. I prepared it. This is called clown underscore lumi dot bmp, and I want to see the actual size of a 512 by 512. This is the actual size in pixels of a 512 by 512 image. Pay a good attention here. This is a very small in dimension image. This image is very, very small. If you want to print it, you cannot print it as a poster. You cannot print it on a very big frame. You cannot have it on your wall because it will be very small but when you print it. Okay, so this is a very small image. You can see it on the screen that it occupies my screen, but in fact, this image is small when you want to print it. Okay, so let us zoom a little bit this image to see that each time I zoom, the pixels will get bigger, and I can see that every pixel have different color in the grayscale. Okay, this is my image. I will zoom back to actual size. I will show you. I open this image from here. Look at me to the features of this image. This image is of dimension 512 times 512. It is written that it is a Windows bitmap image. So already you know something now. You know that the .bmp format is a Windows property format. It is not, for example, an open format. This is a property for Windows, BMP. And now you can see how much is the size of this image. It is 263 kilobytes. So did I calculate this size? In fact, this is a format, so this is not straightforward calculation. But suppose I want to calculate this size. It is easy. We have 512 times 512 pixels. Each pixel occupies 8 bits, so times 8. It will give me 260 144 bits. If I want to know the number of bytes, I divide by 8 and I will get 32,000 bytes, which is approximately, if I divide, okay, which is approximately a quarter of megabyte, okay, a little more than a quarter of megabyte. If I have a 512 times 512, but not grayscale image, if it is, for example, a color image, for which a pixel is on 24 bits, so I will have, instead of multiplying by 8, I multiply by 24, so the final size will be multiplied by 3, and thus a color image of the same size. Remember that I have told you that this is a very small image. It will occupy a 3/4 of a megabyte. And we are talking now theory. This is no compression. Okay, the files I already showed you, they have compression because every format, every picture file format has a certain compression. Look at me to the picture I have in my folder. I have JPEG pictures, I have BMP pictures, I have GIF pictures. Some of them are colored, some of them are not colored, are grayscale. I have also black and white pictures, and we will dealing with a lot of pictures. And look, here we have TIFF pictures, TIF, PNG. All of these are file formats to represent a picture. Now here in this slide I am talking to you how to calculate the theoretical size of an image without compression, but in reality we will study together in this course how there exist file formats, and for each format there is a theory behind. They say we will represent a pixel on 8 bits, no on 6 bits, no, okay, we will represent it on 8 bits, but we will compress it later. And thus, without compression, a very small color image will occupy almost a megabyte. So modern high digital cameras, remember, they are not 512 times 512. Modern high digital cameras, anyone in his smartphone, look up at the properties of your camera. It is minimum 12 megabyte pixels. Okay? And they will produce, every time you shoot yourself a selfie, you will get, if there is no compression, you will get a 28 megabyte picture. Imagine how many pictures you shoot yourself a day or you shoot a day, and deduce with me that we need to compress these pictures, otherwise we will have full disks. Audio signals is another type of media, and this is before digitizing a continuous analog signal. You are listening to my voice now. My voice is a signal. It is a continuous analog signal which is input through the microphone in the presentation and digitized and stored. It is stored on the video, inside the video, and you are listening to it as a digitized. We can distinguish CD quality audio, which is stored on 16 bit sampling at 44.1 kilohertz, or even higher audio fill rates. So we can have 24 bit, 96 kilohertz. What is kilohertz? It is the number of sample per second. How many sample? Because from analog, I have to transform it to digital. So instead of taking all the signal, I will take some samples of the audio signal at different moments. So how many samples per signal? This is the kilohertz. As an example, if you have mono and stereo is the double of mono because you can take from two sources. 1 minute mono CD audio quality. If it was uncompressed, if I talk for 1 minute on mono quality, it will be 5 megabyte. And for stereo, it will be the double. So also this media is usually compressed. It is no way that we deal with it uncompressed. We arrive at video. What about video? The input is analog video captured by video camera. Okay, you are outside, you are playing, you are having a party, a picnic, so you decide to capture this moment and digitize it. Automatically it will be digitized since you are using a digital camera. And the format are a variety. You can before digital camera, you can capture it using analog camera or with digital camera. Raw video are series of single image. Imagine with me what is a video. In fact, it is a series of images, one image after the other. Normally, how many images per second we take? We take 25, 30 or 50 image per second. We say inside the video the image is called now frame. So we talk about frames per second. As a storage example, we take one frame. It will be of the size, if for the same dimensions as before, it will be a quarter of megabyte. We have per second 25 of these frames, so 25 times 0.25, it will be 6.25 megabyte. It is only 6 megabyte only for 1 second. What can you say in 1 second? Nothing of uncompressed video. Typical PAL digital video will have different dimensions and will thus result in 30 megabyte per second. If this uncompressed, I repeat, because no one deals with uncompressed video, and this slide is made specially to show you that we should compress multimedia data. High definition DVD with 1440 pixels width, 1080 pixels height, and now you can see these numbers. These numbers are not from my head. These numbers are standards. If you say PAL, this is the dimension. If you say high definition DVD, this is the dimension. Every standard, every format has its dimension, has its defined width and height. And thus we continue by the example. For an HD DVD, 1 second only needs 112 megabytes. So the last point is obvious. Digital video clearly needs to be compressed. Those are the common property that the medias must be digital. They are all voluminous. They have to be interactive. So you have to have the choice to interact with the content. You want to read the text, even the text you want to read. You want to be able to skip some paragraphs and go to the end. The video is the same thing. The audio is the same thing. It is not a beautiful idea to deal with medias that are not interactive. No one wants to listen to my lecture from A to Z without pausing it, without rewinding it, or skipping some paragraphs. And it have to be real-time and synchronization, real-time requirements and resulting synchronization. You cannot support to use the media that are not synchronized or that are not rendered in real time. So if it takes me 1 second to say a word, you have to listen to it during 1 second. You can, of course, fasten or slow, but these are requirements. So those are the core designs to good working multimedia applications. Next, to finish this section, we will discuss compression. I already introduced to discussion. From the book, I took this table 2.1. Those are some values for standard definition and for high definition. Again, we see the numbers, and we see here not 25 frames per second, but 30 frames per second. So you do the multiplication, and for an hour, you conclude for a standard definition video, you need 100 gigabytes for only 1 hour. And for a high definition video, because you all like to watch HD videos, you don't like low quality, so it will be 6 times more in storage. So we need an excellent and fast data compression, and luckily we already have this data compression since before 2000. How much compression is required? It depends on application, capability of viewing and display, and bandwidth. It depends on the application first, because if you are viewing this media from a small application, from an application on a small smartphone, you don't need it to be high definition because it will not fit on your screen either ways. It will be downsampled. Um, Also on the bandwidth, sometimes when you watch YouTube, you explicitly choose to down the quality because you don't want to spend all your internet subscription with to view only one small video, and those are factors. In JPEG, amount of compression can be controlled. Luckily, you have a Q value. You can decide if you put Q equal 100, you will get the image in its best quality, versus Q equal 0, it is the worst possible quality for the JPEG image. And you can see the percentage of the original and the compressed file. If you get a Q in the original, the file size will be 530, for example, megabyte. A Q factor equal to 75. Look with me how much it is reduced. How much? If you reduce the quality a little bit, 25%, how many of the original instead of 100, only 7% of the original size will be occupied. For Q quality less, you have for sure lesser size. And as visual example for this table, also extracted from the book, see with me the original image. Okay, I will try to zoom. So this is the original image. Of course, now it is all inside a JPEG, so it is tethered. This is the worst case quality with Q equal 5. You can see that no much details are left, but with Q equal 25, which is very good image, nobody will notice. If your brother or sister is in holiday and is sending you pictures, you can see that they are inside a very beautiful city, and that they are enjoying their time, and that the roofs are red and the nature is green and there is a river and a blue sky. So, and how much size you gained? A lot of size. Instead of 530 kilobytes, you get, or megabytes or whatever, you get 16 only 16. So to reduce file size, we convert to different kinds of file format, and those are the compression techniques: standard, JPEG, for images and pack for video. We will be studying all these together. And for speech, there are compression techniques also, and for audio, and also for text. So every kind of media has its compression technique that is for him. And average file sizes are given here. You can see that it will be reasonable. This is the end of the second section of the chapter. Excuse me for mistakes in pronunciation. This happens, and next we will be discussing the third and last section of the chapter 1.